I did a calculation once. Simple, honest, straightforward calculation, the kind you'd give a decent graduate student on a Tuesday afternoon. Add up the energy. That's all it was. Add up the energy sitting in empty space, the way quantum mechanics says you must. I followed the rules. I trusted the mathematics, and the answer I got told me the universe should have ripped itself to shreds about a billionth of a billionth of a billionth of a second after it began. Not might have, should have. According to the best theory we've got, the theory that predicts the magnetic moment of the electron to 12 decimal places, the most accurate theory human beings have ever produced. Empty space should contain so much energy that reality as you know it is impossible. You, me, the stars, the galaxies, the chair you're sitting in, none of it should be here. And yet, here we are. So either the universe is wrong or we are. And I want to spend some time with you figuring out which one it is. Let's start with something that sounds crazy, but is absolutely true. Empty space is not empty. I know that sounds like a contradiction. If it's empty, how can it not be empty? But quantum mechanics is very clear about this, and it has been verified so many times in so many experiments that there's no wriggling out of it. Take a box, pump all the air out, remove every atom, every photon, every particle of any kind. Cool it down to absolute zero. You have made the emptiest thing you can possibly make. And quantum mechanics says there is still energy in that box. It cannot be removed. It is built into the fabric of space itself. Why? Because of something called the uncertainty principle. You cannot simultaneously know the exact position and the exact momentum of anything. That includes fields. An electromagnetic field, say, cannot just sit perfectly still at zero. If it did, you'd know its value exactly and its rate of change exactly, both at the same time. Nature does not allow that. So even in the ground state, even when everything is as calm as it can possibly be, the field jitters. It fluctuates. It buzzes with a tiny residual energy that can never be taken away. We call this zero-point energy, and it's real. Not theoretically real, not philosophically real. Experimentally, physically, get your hands dirty real. You can measure its effects. There's an experiment, a beautiful one, first predicted by a fellow named Casimir back in 1948. Take two perfectly flat metal plates and bring them very close together in a vacuum. I mean close. Fractions of a micrometer apart. The plates will attract each other. Not because of gravity, which is far too weak at that scale. Not because of static charge, which you can screen for. They attract because of the zero-point fluctuations of the electromagnetic field. Here's the picture. Outside the plates, the electromagnetic field can vibrate at any wavelength it likes. Between the plates, only certain wavelengths fit. Long wavelengths that don't match the gap are excluded. So there are more modes pushing in from the outside than pushing out from the inside. The plates get squeezed together by a tiny but real force. People have measured it. It matches the prediction to within a few percent. The vacuum is not empty. That much we know for sure. It is one of the cleanest confirmations of quantum field theory we have. So here is our first clue. Empty space has energy. A tiny bit per mode, 1/2 times the frequency times Planck's constant for each mode. Not much for any single vibration. But how many modes are there? This is where the trouble begins. A quantum field doesn't just vibrate at one frequency, it vibrates at every frequency. Think of it like a guitar string, except this string has no ends. It can vibrate in waves of any wavelength you like. Long, lazy waves, short, frantic ones. Waves within waves within waves. Each possible vibration is a mode. Each mode carries its 1/2 quantum of energy, and the shorter the wavelength, the higher the frequency, and the more energy that mode contributes. And it's not just the electromagnetic field we have to worry about. Every quantum field contributes. The electron field, the quark fields, the gluon field, the neutrino fields. Every field in the standard model has its own set of zero-point fluctuations, its own set of modes, each one adding its 1/2 quantum of energy to the vacuums. So you start adding them up. You start at the longest wavelengths. Fine, small contributions. You move to shorter wavelengths. The contributions grow. You keep going. Shorter, higher frequency, more energy per mode. And you realize there is no obvious place to stop. Quantum field theory, as we understand it, says these modes keep going to arbitrarily short wavelengths, arbitrarily high frequencies, arbitrarily high energies. The sum diverges. It blows up to infinity. All right? You say, Infinity is probably a sign we're being naive. Maybe physics changes at very short distances. Maybe there's a shortest possible wavelength. Fine. Let's be conservative. Let's say we can trust our theory down to the Planck length, about 10 to the minus 35 meters. That is incredibly small. It is 20 orders of magnitude smaller than a proton. Below that, we need a theory of quantum gravity, which we do not have. So let's cut the sum off there. Even with that cutoff, the energy density you get for the vacuum is staggering. It works out to something like 10 to the 93 grams per cubic centimeter. Let me give you a sense of scale. The entire observable universe, all the galaxies, all the stars, all the gas, all the dust, everything, if you smeared it out uniformly, has a density of roughly 10 to the minus 29 grams per cubic centimeter. The vacuum energy the theory predicts is roughly 10 to the 120 times larger than what we observe. 10 to the 120. That is not a small discrepancy. That is not, oh, we're off by a factor of 2, let's check the arithmetic. That is the single largest disagreement between theory and observation in the history of science. Nothing else even comes close. Let me say that again because I want you to feel the weight of it. Our best theory of particle physics, the one that gets everything else right, predicts a number that is wrong by a factor of 1 followed by 120 zeros. If this were a measurement of the distance from New York to Los Angeles, it would be like predicting the distance is larger than the observable universe. When your theory does everything else beautifully and then makes a prediction that is off by 120 orders of magnitude, something very deep is wrong, or something very deep is going on that you do not understand. This is the cosmological constant problem. Some people call it the vacuum catastrophe. I call it the most disturbing calculation I've ever done. See, the energy of the vacuum isn't just an academic curiosity. In Einstein's theory of general relativity, energy curves space-time. All energy. It doesn't matter where the energy comes from, whether it's the mass of a star, or the heat in a cup of coffee, or the zero-point jitter of a quantum field in empty space. Energy bends the geometry of the universe. And a vacuum energy as large as quantum field theory predicts would curve space-time so violently that the universe could not exist in any form we would recognize. If the vacuum energy were positive and as enormous as the naive calculation suggests, space would expand so rapidly that no particles could ever find each other. Protons would fly apart before they could meet electrons. There would be no atoms, no molecules, no chemistry, no stars condensing from gas clouds, no planets, no oceans, no curious creatures looking up at the sky and wondering about the cosmological constant. The universe would be an empty, exponentially inflating void, stretching itself into oblivion faster than anything could form within it. If instead that enormous energy were negative, the effect would be equally catastrophic, but in the opposite direction. Space-time would curve inward so violently that the universe would collapse back on itself, crumpling into a point in a fraction of a second. Not enough time for a single nuclear reaction. Not enough time for a single thought. Either way, we would not be here to worry about it. The universe we live in requires the vacuum energy to be absurdly, preposterously, almost impossibly small. And yet the actual vacuum energy, the one we measure through the observed acceleration of the expansion of the universe, is incredibly small, almost zero, but not quite zero. That was the surprise when they measured it in 1998. The cosmological constant exists. It is positive. The expansion of the universe is accelerating, but the amount of vacuum energy responsible is smaller than the theoretical prediction by that absurd factor. So you might think, well, maybe the real answer is just zero. Maybe there's some beautiful symmetry that makes all those vacuum contributions cancel out perfectly. That would at least be elegant. But the observations say no, it is not zero. It is a tiny, tiny positive number, as if all those enormous contributions almost cancel, leaving behind a residue so small it is practically nothing, but not actually nothing. That is deeply suspicious. Imagine you owe someone money, a lot of money, and someone else owes you almost exactly the same amount. The two debts almost cancel. The difference between what you owe and what you are owed turns out to be 6 cents. Now, if the amounts involved were both about $10, a 6-cent remainder would not be very surprising. But what if both amounts are $100 trillion, and after this colossal cancellation, the remainder is 6 cents? You would not call that a coincidence. You would suspect the game is rigged. Something is enforcing that cancellation, and you want to know what. That is where we are in physics. Something is canceling the vacuum energy to 120 decimal places, but not perfectly. The first 119 digits cancel. The last one doesn't. We have no idea why. People have tried all sorts of things. Brilliant people. People who've spent entire careers on this one problem. Let me walk you through the main attempts, because each failure teaches us something. Supersymmetry was one hope. The idea is elegant. Every particle has a partner. Every boson, every force-carrying particle, has a fermionic partner with the same mass, and vice versa. Bosons and fermions contribute to the vacuum energy with opposite signs. Bosons push the energy up. Fermions pull it down. If every boson has an exactly matched fermion, the contributions cancel perfectly. The vacuum energy is zero. Beautiful. Except we have never found a single superpartner at the masses we've been able to probe. We built the Large Hadron Collider, the biggest machine in history, partly to look for them. Nothing. Which means if supersymmetry exists, it's broken. The partners exist, but are heavier than their counterparts. And once the symmetry is broken, the cancellation isn't perfect. The contributions don't quite match. You're back to a huge vacuum energy. Supersymmetry at best reduces the problem from 120 orders of magnitude to maybe 60. That is like saying your house is on fire and I've managed to move the fire from the living room to the kitchen. Progress, perhaps, but the house is still burning. Another idea, maybe you can find a field that dynamically adjusts itself to cancel the cosmological constant, a field that notices the vacuum energy is too large and compensates. Steven Weinberg and others explored this, and the problem is always the same. You can build such a model, but it requires fine-tuning that is just as bad as the original problem. You've moved the mystery from one place to another without actually solving it. Others have tried to argue that the vacuum energy simply doesn't gravitate, that gravity somehow doesn't see it. But this is very hard to make work without destroying the rest of general relativity, which has been tested to extraordinary precision. Gravitational lensing, the precession of Mercury, gravitational waves, all confirmed. You can't just tell gravity to ignore one particular kind of energy. There is no mechanism for that doesn't break something else we know is right. Some physicists, and they are serious people, not cranks, have turned to what's called the anthropic argument. The idea is this: maybe the vacuum energy is not a fixed constant of nature. Maybe it takes different values in different regions of a vast multiverse. In most regions, the value is enormous, and nothing interesting happens. No structure, no life, no observers. But in a few rare pockets, the value is small enough for galaxies to form and for beings like us to exist. And of course, we find ourselves in one of those pockets because we could not exist anywhere else. We are, in this view, selecting ourselves into a habitable universe just by being alive to ask the question. I don't love this argument, not because it's illogical, but because it doesn't feel like physics. It explains the observation, yes, but it doesn't explain the mechanism. It's like asking why the water in a particular puddle fits the hole so well, and being told, because if the water didn't fit, it wouldn't be in that hole. True, but unsatisfying. I want to know how the hole got there. I want to see the machinery. And I'll be honest with you, we don't see the machinery, not yet. This problem has been open for decades. Some of the smartest people I've known have worked on it and come away baffled. There is a temptation in physics to pretend that the hard problems are almost solved, that we just need one more clever idea. I'm not going to tell you that. We are stuck. And being stuck on something this fundamental means there is probably a very big idea we are missing. Something about the nature of space-time, or about quantum mechanics, or about the relationship between the two that we simply have not thought of yet. What I can tell you is this: the fact that the universe exists at all, the fact that the vacuum energy is not the monster our equations predict, that is trying to tell us something. Nature has done something extraordinary. It has taken an enormous quantity, a quantity so vast that it would obliterate everything, and it has tamed it. Almost perfectly, but not quite. Whatever mechanism is responsible for that near-perfect cancellation is, in my view, one of the deepest secrets in physics, deeper than quantum gravity, deeper perhaps than anything else we are looking for. When I teach students, I sometimes see them get discouraged when they learn about unsolved problems. They want the textbook to have all the answers, but this is the wrong attitude entirely. Unsolved problems are not failures of physics. They are invitations. They are nature saying, you're clever enough to see the puzzle, now see if you're clever enough to solve it. And the cosmological constant problem is the grandest invitation I know of. It touches everything: quantum mechanics, gravity, cosmology, the structure of space itself. So if you ask me why the universe exists, the honest answer is, I don't know. Nobody does. The mathematics says it shouldn't, and yet it does. And the gap between those two facts contains what might be the most important piece of physics that nobody has discovered yet. You know, someone asked me once, aren't you bothered that you can't figure it out? And I said, are you kidding? It's the most exciting thing in the world. To know that there is a secret, that big sitting right there in the equations, waiting for somebody to see it. Maybe it's you. Maybe it's somebody who hasn't been born yet. But it's there. The universe did something spectacular, and it left us a receipt. We just can't read it yet. If I had to bet, I'd bet the answer is going to be strange. Not just a small correction to what we already know, but something genuinely new. Something that changes the way we think about space and time and energy in a way we can't even imagine right now. Because that's how the big answers always come. Not by patching the old picture, but by realizing the picture was missing a dimension you didn't even know to look for. So tell me, if the equations say the universe shouldn't be here, and you're sitting in it right now, which do you trust? The equations or your own existence? Think about that, and let me know what you decide.